Tonight, we're going to look at one of the strangest possibilities that modern cosmology has been seriously discussing. The possibility that the Big Bang was not the beginning of everything. The possibility that something existed before. The possibility that the universe we observe is not the first universe, but one of many, in a long sequence of cosmic cycles stretching back through enormous timescales that may extend to infinity. This possibility has, for most of the past century, been considered fringe. The Big Bang theory has been the standard cosmological model. The universe in that model began at a specific moment, and there was no before. The question of what came before the Big Bang was, by every careful description, considered meaningless within the standard framework. Time itself began at the Big Bang. There was no cosmic moment to point to as before, but over the past few decades, a small group of theoretical physicists has developed serious alternative models. The most famous is Roger Penrose's Conformal Cyclic Cosmology, often called CCC. Penrose, who won the 2020 Nobel Prize in Physics for his earlier work on general relativity and black holes, has been advocating for CCC since the early 2000s. In his framework, the universe goes through an infinite sequence of cosmic aeons, each beginning with a Big Bang and ending in a state that eventually transitions into the next aeon. The recent JWST observations of the early universe may, in some interpretations, support these alternative models more naturally than they support the standard inflationary Big Bang. By the end of tonight, you're going to understand what Roger Penrose's Conformal Cyclic Cosmology actually proposes, the related cyclic and pre-Big Bang scenarios developed by other major physicists, the specific predictions these models make for cosmic observations, how the JWST observations might bear on these predictions, and what the future cosmic microwave background experiments may eventually reveal about whether the Big Bang was truly the beginning of everything or just one moment in a much longer cosmic history. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the standard Big Bang model and why we believed it. The standard cosmological model was not handed down from above. It was built up over the course of a century through a sequence of observations and theoretical developments that gradually converged on a coherent picture. Each piece of the model was added because it explained something specific about the universe that the existing theory could not. The first major piece was the discovery of cosmic expansion. Edwin Hubble, working at the Mount Wilson Observatory in California, published a paper in 1929 titled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. Hubble showed that distant galaxies were receding from us at speeds proportional to their distance. The further away a galaxy was, the faster it was moving away. This was, by every careful estimate, one of the most consequential observations in the history of astronomy. It established that the universe was not static. It was expanding. Galaxies were getting further apart. The expansion was happening everywhere, in all directions, with no preferred center. The implication was profound. If the universe is expanding now, it must have been smaller in the past. If you trace the expansion backward, eventually the entire observable universe would have been compressed into a much smaller volume. At some point in the deep past, the universe would have been compressed into an extremely hot, dense state. The Belgian priest and physicist Georges Lemaitre recognized this implication. In a paper published in 1931, Lemaitre proposed what he called the primeval atom hypothesis. The universe, in his framework, began as a single extremely dense entity, that exploded and expanded into the cosmos we observe today. Lemaitre's proposal was the conceptual foundation of what we now call the Big Bang model. The name Big Bang itself was coined later, in 1949, by the British astronomer Fred Hoyle. Hoyle used the term dismissively during a BBC radio broadcast. He was an advocate of the competing steady-state theory, which proposed that the universe was eternal and unchanging on large scales. Hoyle thought the idea of a definite cosmic beginning was philosophically problematic. He preferred the elegance of a universe that had always existed. Hoyle's dismissive label, ironically, became the standard name for the cosmological model that eventually displaced his own preferred theory. The second major piece of evidence for the Big Bang came in 1965. Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in Holmdel, New Jersey, were attempting to characterize the background noise in a microwave radio antenna they were preparing for satellite communications work. They found an unexplained excess of microwave radiation coming from all directions in the sky. The radiation had no apparent source. It was the same intensity from every direction. After checking every possible source of contamination, including a population of pigeons that had been nesting in their antenna, Penzias and Wilson concluded that the radiation was real and cosmic in origin. At the same time, a team at nearby Princeton University, led by Robert Dicke, had been theoretically predicting that the Big Bang should have left a relic radiation signature in the form of a cosmic microwave background at a temperature of about a few degrees above absolute zero. When Penzias and Wilson described their observations to the Princeton team, the connection was immediate. The mysterious microwave radiation was the cosmic microwave background predicted by Big Bang theory. The discovery established the Big Bang as the dominant cosmological framework. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. The cosmic microwave background has been studied in progressively greater detail ever since. The COBE satellite in the 1990s confirmed that the CMB had a near-perfect blackbody spectrum, with tiny temperature variations across the sky. George Smoot and John Mather shared the 2006 Nobel Prize for the COBE results. The WMAP satellite in the early 2000s and the Planck satellite from 2009 through 2013 produced increasingly precise maps of the CMB temperature variations. The detailed pattern of those variations encodes information about the conditions in the early universe. The third major piece of evidence for the Big Bang is the abundance of light elements. Big Bang nucleosynthesis, worked out theoretically by Ralph Alpher, George Gamow, and Robert Herman in the late 1940s, predicts that the very early universe should have produced specific amounts of hydrogen, helium, and lithium through nuclear reactions in the first few minutes after the Big Bang. The predicted abundances match the abundances observed in the most pristine cosmic gas to high precision. The match is, by every careful estimate, one of the strongest pieces of evidence for Big Bang cosmology. With cosmic expansion, the cosmic microwave background, and Big Bang nucleosynthesis all consistent with the Big Bang framework, the model became the standard cosmological framework by the late 1970s. But the standard Big Bang model had specific theoretical problems that needed to be solved. The model required very specific initial conditions to produce the universe we observe. The cosmic microwave background is extremely uniform across the sky, with temperature variations of only 1 part in 100,000. The universe is also remarkably flat geometrically, with the total mass-energy density very close to the critical density needed for flat space. Both of these properties require precise initial conditions that the basic Big Bang model could not naturally explain. These puzzles motivated the development of inflationary cosmology in the early 1980s. Alan Guth at MIT and Andrei Linde at the Lebedev Physical Institute in Moscow proposed that the very early universe underwent a brief period of exponential expansion called inflation. During inflation, the universe expanded by a factor of more than 10 to the 26 in a tiny fraction of a second. This rapid expansion smoothed out any initial irregularities, producing the uniform and flat universe that we observe. Inflation also produced quantum fluctuations that were stretched to cosmic scales, becoming the seeds of all later cosmic structure. The inflationary model has been the standard framework for understanding the very early universe for more than 4 decades. The model is, by every careful description, remarkably successful. It explains the uniformity of the CMB, the flatness of cosmic geometry, the absence of magnetic monopoles, and the spectrum of primordial density variations. The predictions of inflation match the observations to high precision. By the 1990s, the combination of Big Bang cosmology with inflation had become the unchallenged standard model of the universe's origin. But every standard model in physics eventually encounters problems that motivate alternatives. The standard inflationary Big Bang model is no exception. Over the past 4 decades, a growing list of theoretical and observational concerns has motivated some physicists to seriously consider alternative cosmologies. These alternatives do not necessarily reject the basic framework of cosmic expansion from a hot, dense beginning. They reject specific features of the standard model. Some reject inflation in favor of other mechanisms for solving the horizon and flatness problems. Some reject the very idea of a singular Big Bang beginning in favor of a cyclic or eternal universe. The question of what came before the Big Bang has, in this sense, become a serious topic of theoretical investigation rather than a fringe speculation. The standard model remains dominant, but it is not unchallenged. The most thoughtful challenges come from physicists with established reputations and serious theoretical credentials. Roger Penrose is one of them. But here are the puzzles that the standard inflationary Big Bang model still has not resolved, and that motivate cosmologists to consider alternatives. The first puzzle is the singularity itself. The Big Bang model traces cosmic expansion backward in time and finds that at a specific moment, approximately 13.8 billion years ago, the entire observable universe was compressed into a state of infinite density and infinite temperature. This is called the initial singularity. The mathematics of general relativity, when applied to the early universe, predicts this singularity. The cosmic density, temperature, and curvature all become infinite as you approach the moment of the Big Bang, but infinities in physics are usually signs that the theory has broken down. Real physical systems do not have infinite densities. The appearance of the singularity in the Big Bang model is, by every careful description, a signal that general relativity alone cannot describe the very earliest cosmic moments. Something else, presumably some form of quantum gravity that we do not yet possess, must take over near the moment of the Big Bang. What that something is and what it implies for cosmic origins remains one of the deepest unsolved problems in theoretical physics. The second puzzle is the cosmological constant problem. Dark energy, the component of the universe that drives cosmic acceleration, has a specific measured value that is approximately 10 to the 120 times smaller than what quantum field theory naively predicts for the energy of empty space. This discrepancy is, by every careful estimate, the largest disagreement between theory and observation in all of physics. The factor of 10 to the 120 is so enormous that the standard model effectively has no explanation for why dark energy has the value we measure. Some mechanism must be cancelling almost all of the predicted vacuum energy, leaving only a tiny residual amount. What that mechanism might be and how it produces exactly the right amount of residual dark energy to drive cosmic acceleration without overwhelming all cosmic structure is one of the great mysteries of modern cosmology. The third puzzle is the multiverse implication of inflation. Most modern inflationary models predict not just a single inflating universe, but an entire multiverse of inflating bubbles. The mechanism that drives inflation in any given region of space is unlikely to ever turn off completely. Instead, inflation continues forever in some regions, producing new universes through a process called eternal inflation. The implication is that our observable universe is just one of an infinite collection of universes, each with potentially different physical properties. This multiverse picture is, by every honest description, philosophically uncomfortable. It suggests that questions about why our universe has the specific properties we observe are unanswerable, because the answer is simply that all possible universes exist, and we happen to live in one with the properties that allow our existence. Many physicists, including some of the original developers of inflation, have become uncomfortable with this implication. Paul Steinhardt, who co-developed the new inflation model in 1982 with Andreas Albrecht, has in more recent years become a prominent critic of inflation precisely because of the multiverse implication. The fourth puzzle is the entropy of the early universe. The Big Bang model requires the early universe to have had extraordinarily low entropy, much lower than would be expected from random initial conditions. The universe at the Big Bang was in a remarkably ordered state, with very low gravitational entropy. The subsequent expansion and structure formation have increased the entropy enormously, but the starting point was, by every careful estimate, anomalously ordered. Why the universe started in such a low entropy state is not naturally explained by the standard inflationary model. Inflation, in fact, requires its own low entropy initial conditions to operate, which simply shifts the question one step deeper without resolving it. Roger Penrose has been particularly vocal about this entropy problem. He has argued that the standard inflationary picture requires more fine-tuning, not less, than the simple Big Bang model it was supposed to improve upon. The fifth puzzle is the unobservability of the inflationary epoch itself. Inflation is supposed to have occurred during a tiny fraction of a second at the very beginning of the universe, at energy scales far beyond anything our particle accelerators can probe directly. The signatures of inflation in the cosmic microwave background are subtle and require very precise observations to detect. The detailed mechanism of inflation, including what field drove it and how it ended, remains uncertain even after 4 decades of theoretical work. Despite many specific inflationary models that have been proposed, none has been definitively confirmed. The model is, by every careful description, robust in its general predictions, but vague in its specific implementation. The sixth puzzle is the more recent set of cosmological tensions revealed by precision observations. the Hubble tension, the persistent disagreement between local and cosmic microwave background measurements of the cosmic expansion rate, suggests that something in the standard cosmological model may need refinement. The S8 tension, the disagreement between cosmic microwave background and weak gravitational lensing measurements of cosmic structure clumpiness, suggests something similar. The recent DESI dark energy results from 2024 and 2025, which hint that dark energy may be evolving rather than constant, add another tension. The JWST observations of an unexpectedly active early universe, which we have discussed in previous evenings, add yet another. Each of these tensions is, by itself, moderate in size. Together they form a pattern that suggests the standard model may need substantial revision. Whether any of these tensions specifically point toward a pre-Big Bang scenario is, by every honest description, not yet established. But they do suggest that the standard model is not the final word. The community is, in some sense, ready to take alternatives more seriously than it has in decades. The seventh puzzle is the question of what selects the specific physical constants and laws we observe. Why is gravity as strong as it is and not stronger? Why is the proton mass what it is? Why is the cosmological constant the size it is? The standard model of particle physics has approximately 20 free parameters, whose values are measured rather than derived from first principles. The values are remarkably specific, with subtle balances that allow stars and planets and life to exist. If the values were slightly different in any of several directions, the universe would be sterile. This apparent fine-tuning has been called the anthropic principle, although the term is often used in confused ways. Whatever you call it, the question of why the specific constants we observe are what they are remains, by every honest description, unanswered by the standard model. Pre-Big Bang scenarios offer one possible angle on this question. If the universe undergoes cycles, the physical constants might be reset or selected at the transition between aeons, with different cycles potentially having different constants. The cycle we observe might be one in which the constants happen to allow life. Other cycles might have had different constants and different histories. Whether this is a satisfying explanation or just a deferral of the question is, by every honest description, philosophically contested. But it is at least a framework within which the question can be approached. Each of these 7 puzzles is independent, but together they form the motivation for the serious theoretical investigation of pre-Big Bang and cyclic cosmologies that has accelerated over the past 2 decades. The standard model is not failing, it still explains an enormous range of observations to high precision. But it has gaps. The gaps motivate alternatives. The alternatives are taken seriously by some prominent physicists, even if the broader cosmological community remains skeptical. The most fully developed of these alternatives is Roger Penrose's Conformal Cyclic Cosmology. Roger Penrose is, by any reasonable measure, one of the most distinguished theoretical physicists of the past half-century. He was born in 1931 in Colchester, England, into an academic family. His father, Lionel Penrose, was a prominent psychiatrist and geneticist. His brother Oliver Penrose became a mathematical physicist. Roger studied mathematics at University College London, then completed a PhD in algebraic geometry at the University of Cambridge in 1958, working under William Valence Douglas Hodge. Penrose's early career was in pure mathematics, but he became interested in mathematical physics and eventually in cosmology and general relativity. He held positions at Princeton University, the University of Texas, Birkbeck College in London, and eventually the University of Oxford, where he became the Rouse Ball Professor of Mathematics in 1973. Penrose's contributions to theoretical physics are, by every careful description, foundational. His 1965 paper on gravitational singularities in collapsing matter established the modern framework for understanding black holes. Penrose showed mathematically that under quite general conditions, the gravitational collapse of a sufficiently massive object must produce a space-time singularity. The result, called the Penrose singularity theorem, was one of the most important results in general relativity since Einstein's original work. Subsequently, Penrose worked with Stephen Hawking to extend the singularity theorems to include the Big Bang itself. The Penrose-Hawking singularity theorems, published in the late 1960s, established that the standard Big Bang model necessarily includes an initial singularity under quite general assumptions about the cosmic content. Penrose's mathematical work extended far beyond cosmology. He developed the twistor theory of spacetime in the 1960s, providing a new mathematical framework for thinking about general relativity. He proposed the cosmic censorship conjecture, which states that singularities in general relativity must be hidden inside event horizons, except in very specific circumstances. He created the Penrose tiles, mathematical patterns that tile the plane non-periodically, which later turned out to have applications in quasi-crystals. He proposed the Penrose process, a mechanism for extracting rotational energy from a rotating black hole. He developed the conformal compactification of spacetime, which represents infinite distances as a finite mathematical boundary, providing tools for analyzing the global structure of cosmological spacetimes. In 2020, the Royal Swedish Academy of Sciences awarded Penrose the Nobel Prize in Physics. The citation specifically mentioned his 1965 work on singularities in collapsing matter, recognizing that this work provided the mathematical foundation for the modern understanding of black holes. Penrose shared the prize with Reinhard Genzel and Andrea Ghez, who had observed the supermassive black hole at the center of the Milky Way. Penrose was 89 years old at the time of the award. He has continued to work actively on cosmological and mathematical questions into his 90s. Penrose's path to conformal cyclic cosmology came through his long-standing concern about the entropy problem in cosmology. As we discussed in the previous pivot, the Big Bang requires the early universe to have had extraordinarily low entropy. Penrose has, in numerous papers and books over several decades, argued that this low entropy initial condition is not naturally explained by inflationary cosmology. Inflation, in his view, requires its own low-entropy initial conditions to operate. The entropy problem is simply shifted backward in time rather than resolved. Penrose was, by every careful description, unsatisfied with this state of affairs. He spent years thinking about how the universe might have started in a low-entropy state, without requiring fine-tuned initial conditions. In 2005, Penrose proposed his Conformal Cyclic Cosmology in a series of lectures at the University of Oxford. The framework was published in detail in his 2010 book Cycles of Time, an extraordinary new view of the universe. The book was aimed at a general audience but contained substantial technical content. Penrose has, in the years since, continued to develop and defend the framework in academic papers and public talks. The basic idea of CCC is that the universe goes through an infinite sequence of cosmic aeons. Each aeon begins with a Big Bang. Each aeon ends after enormously long cosmic time in a state where the universe has expanded so much that all the matter has effectively dispersed and the cosmic temperature has dropped to nearly zero. This final state in Penrose's framework is mathematically equivalent to a fresh, hot Big Bang state, allowing a transition to the next aeon. The mathematical trick that makes CCC work is called conformal rescaling. Penrose argued that the very late universe and the very early universe are mathematically similar in specific ways. Both states are dominated by massless radiation. In the very late universe, all matter has presumably decayed into radiation through processes like black hole evaporation. In the very early universe, before the formation of atoms and structures, the universe was filled with energy in the form of massless or near-massless particles. Both states have specific geometric properties that allow them to be connected through a conformal transformation, which is a specific mathematical operation that preserves angles but changes scales. The conformal rescaling in Penrose's framework smoothly connects one cosmic aeon's distant future to the next aeon's earliest past. Time does not literally restart in the new aeon, it continues but with different scale factors. The mathematical continuity is, by every careful description, the central feature of CCC. The framework provides a specific mechanism for the universe to transition from one aeon to the next without invoking any genuinely new physics, beyond the carefully worked-out conformal mathematics. Penrose's motivation for CCC was, by every careful description, partly aesthetic. He wanted a cosmology that was mathematically elegant and that did not require fine-tuned initial conditions. The cyclic framework provides this. Each cosmic aeon starts with conditions that are the inevitable result of the previous aeon ending. The starting conditions are not arbitrary or fine-tuned. They are determined by the dynamics of the previous cycle. The entropy problem is, in Penrose's view, addressed because the low entropy at the start of any given aeon is not a coincidence, but a consequence of how the previous aeon ended. The framework also addresses the multiverse implication of inflation. CCC does not require eternal inflation or a multiverse of bubble universes. The cyclic structure provides a different way to address the cosmological initial conditions problem. Penrose has argued that this makes CCC more philosophically satisfying than inflation. Whether his arguments are persuasive depends, by every honest description, on philosophical preferences as much as on observational evidence. But the framework is taken seriously by Penrose and a small group of collaborators because of its mathematical elegance and its conceptual handling of the initial conditions problem. CCC is not, by every careful description, widely accepted in the broader cosmological community. Most cosmologists prefer the standard inflationary framework, despite its difficulties, because it has been more thoroughly developed and because its predictions match the observations more straightforwardly. CCC remains a minority position, but it is a minority position advocated by one of the most distinguished theoretical physicists alive, with serious mathematical work behind it. The framework is taken seriously enough that other prominent cosmologists have engaged with it, either supportively or critically, in numerous published papers and public discussions. Penrose has continued to refine CCC and to search for observational evidence that might support it. The search has focused on specific predictions that CCC makes for what we should observe in the cosmic microwave background and elsewhere. These predictions and the controversial claimed detections that have followed are the subject of the next part of our discussion tonight. Let's go deeper into what CCC actually proposes and what makes it mathematically work. The framework rests on several specific ideas that come together to make the cyclic universe picture coherent. The first idea is conformal geometry. Standard general relativity describes space-time through a metric, a mathematical object that tells you the distance between any two nearby points. The metric encodes both angles and scales. If you know the metric, you know how long things are and how much they bend toward each other. Conformal geometry, by contrast, throws away the scale information and keeps only the angle information. Two spacetimes are conformally equivalent if their angles match, regardless of whether their scales match. The mathematical machinery for working with conformal geometry was developed extensively in the 20th century and is, by every careful description, a well-established branch of mathematics. Penrose's insight was that conformal geometry might be the natural framework for understanding the connection between the end of one cosmic aeon and the beginning of the next. The end of a cosmic aeon in CCC is a state where the universe has expanded so much that all matter has effectively dispersed. Through processes like black hole evaporation via Hawking radiation, even the most massive cosmic structures eventually decay into radiation. Over enormously long timescales, perhaps a googol years or more, the universe approaches a state where everything has become essentially massless radiation. In this final state, the universe has no clocks. The notion of time becomes ambiguous because all the matter that would have allowed us to measure time has disappeared. The geometry of space-time in this final state is dominated by the conformal structure rather than by the absolute scale. Penrose's argument is that this final state is mathematically equivalent, through a conformal transformation, to the initial state of a fresh cosmic aeon. The initial state of any cosmic aeon in standard Big Bang cosmology is a state of extremely high temperature where all matter has been ionized into a plasma of massless or near-massless particles. The geometry of this initial state is also dominated by the conformal structure, rather than by absolute scales. The two states, despite occurring at opposite ends of cosmic history, share the property of being dominated by massless radiation and having ambiguous scales. The conformal transformation that connects them is, in Penrose's framework, the mathematical operation that allows one aeon to transition into the next. The transformation rescales the very large distances of the late universe to become the very small distances of the early next universe. Time does not literally restart. The framework treats the end of one aeon and the beginning of the next as a single mathematical entity, viewed through different conformal lenses. The specific mathematical claim is that the Weyl curvature tensor, a particular measure of how spacetime is curved by tidal effects, vanishes at the conformal boundary between aeons. Penrose proposed the Weyl curvature hypothesis in the 1970s before he developed CCC. The hypothesis states that the Weyl curvature was zero at the Big Bang, which would mean the early universe started in a state with no tidal gravitational distortion. This zero Weyl curvature condition, combined with the conformal rescaling framework, provides the technical foundation for CCC. The Weyl curvature hypothesis is, by every careful description, controversial. Most cosmologists are not convinced that the Weyl curvature was exactly zero at the Big Bang. But Penrose has argued in numerous papers and books that the hypothesis is required for a satisfactory cosmological framework that does not invoke fine-tuned initial conditions. The hypothesis is, in his view, motivated by deep theoretical considerations, even if it cannot yet be directly tested. The second key idea in CCC is the inevitability of the late universe state. Penrose argues that the dynamics of cosmic expansion combined with dark energy and the eventual evaporation of black holes must lead to a final state where the universe consists entirely of dilute, massless radiation. This is, by every careful estimate, a robust prediction of standard cosmology over enormously long timescales. The current era of cosmic structure is just a small slice in cosmic history. Over the next many tens of billions of years, dark energy will continue to drive cosmic expansion. Galaxies will become increasingly isolated, star formation will eventually cease, stars will burn out. Black holes will form and grow. Over much longer timescales, black holes will themselves evaporate through Hawking radiation, releasing their mass energy as photons. After approximately 10 to the 100 years, even the most massive black holes will have completely evaporated. The universe will be filled with dilute photons and other massless particles with no remaining structure on any scale we would recognize. This is the late state that CCC requires. Penrose argues that this state, properly analyzed conformally, is equivalent to the initial state of a new cosmic aeon. The transition is, in his framework, not a physical event in the conventional sense. It is a mathematical equivalence that becomes meaningful once the universe enters the appropriate state. The third key idea is the conformal mapping itself, the specific mathematical operation that connects the end of one aeon to the beginning of the next is well defined within Penrose's framework. The framework uses a specific conformal factor that rescales the very large late universe distances to become small early universe distances. The mathematical details have been worked out by Penrose and his collaborators in numerous technical papers. The framework is, by every careful description, mathematically consistent within its own assumptions. Whether the assumptions are physically realized in our universe is the open question. Critics of CCC have pointed out several issues with the framework. The first issue is whether the necessary conditions for the conformal transition are actually achieved in our universe. In particular, the existence of even a single massive particle in the late universe would prevent the clean, conformal rescaling from working. Some massive particles might survive forever in standard cosmology, depending on the specific properties of dark matter and other components. Penrose has addressed this by proposing that dark matter might be unstable on very long timescales, or that some other mechanism converts all mass to radiation in the deep future. Whether such mechanisms actually exist is, by every honest description, not established. The second issue is whether the CCC framework can accommodate observed cosmic structures. Penrose argues that the early universe in our current aeon should bear traces of the late universe of the previous ion. The most striking predicted traces are circular patterns in the cosmic microwave background coming from supermassive black holes that existed and evaporated in the previous aeon. These traces, called Hawking points, would be specific observable signatures of CCC. The search for Hawking points and other CCC signatures has been the focus of substantial observational work. The third issue is whether CCC actually solves the entropy problem it was designed to address. Critics have argued that the conformal rescaling does not really avoid the need for low entropy initial conditions, just hides the issue in a different mathematical formulation. Penrose has defended CCC against these criticisms, but the debate remains, by every careful description, ongoing. Despite the open questions, CCC has the distinct advantage of being a fully developed alternative cosmological framework. Most other pre-Big Bang scenarios are less complete in their technical details. CCC, whether correct or not, has been worked out in enough detail that specific predictions can be made and tested. The framework is, in this sense, a model of how alternative cosmological frameworks should be developed if they want to be taken seriously by the broader community. The specific predictions of CCC and the observational evidence that has been claimed for or against them are what we turn to next. Let's go deeper into the mathematical content of CCC, because the framework's mathematical structure is where its strongest claims and its most controversial aspects both reside. The central mathematical object in CCC is the conformal transformation. A conformal transformation is, by every careful definition, a mapping that preserves angles but not distances. Two geometric configurations are conformally equivalent if you can transform one into the other while keeping all the angles intact. Penrose's insight was that the very late universe and the very early universe, despite occurring at opposite ends of cosmic time and despite having vastly different physical conditions, are conformally equivalent in a specific mathematical sense. The mathematical framework Penrose uses is called conformal compactification of spacetime. Conformal compactification is a technique Penrose developed in the 1960s for analyzing the global structure of spacetimes. The technique involves applying a conformal transformation that maps an infinite spacetime to a finite mathematical region with a well-defined boundary. The boundary represents the asymptotic behavior of the spacetime at infinity. Penrose's diagrams, called Penrose diagrams, use this technique to provide finite representations of infinite spacetimes. The diagrams have become standard tools in general relativity and are taught in introductory courses on black holes and cosmology. In the context of CCC, the conformal compactification provides a precise mathematical framework for describing the boundary between cosmic aeons. The very late universe of one aeon, when conformally compactified, has a specific boundary that Penrose argues is mathematically equivalent to the boundary structure of the very early universe of the next aeon. The two boundaries can be identified through the conformal transformation, providing a smooth mathematical connection between the aeons. The Weyl curvature hypothesis is, by every careful description, central to the CCC mathematics. The Weyl curvature tensor is a specific component of the spacetime curvature that describes tidal effects and the propagation of gravitational waves. The Weyl curvature is mathematically distinct from the Ricci curvature, which describes the local effects of matter on spacetime geometry. Penrose proposed in the 1970s, well before CCC, that the Weyl curvature should have been zero at the Big Bang. This Weyl curvature hypothesis is, in Penrose's view, required to explain the extreme low entropy of the early universe. The reasoning is that low gravitational entropy corresponds to small Weyl curvature, and the universe must have started in a low entropy state to permit subsequent thermodynamic evolution. The Weyl curvature hypothesis is controversial because it cannot be directly tested. The conditions at the Big Bang are not observationally accessible. The hypothesis is, by every careful description, a theoretical claim that constrains acceptable cosmologies. CCC requires the Weyl curvature hypothesis to hold not just at the original Big Bang, but at the start of every cosmic aeon. The conformal transition between aeons must produce a new aeon with vanishing Weyl curvature at its start. The mathematical machinery of CCC ensures this through the specific form of the conformal transformation. The detailed calculations involved in setting up CC are, by every careful description, technical. They involve solving the Einstein field equations in the conformally compactified spacetime, identifying the appropriate boundary conditions, and verifying that the conformal transition preserves the necessary physical properties. Penrose and his collaborators have published numerous technical papers working through these calculations. The mathematical consistency of CCC within its own assumptions is, by every careful estimate, established. The framework does not have internal contradictions when treated as a mathematical structure. The question is whether the framework corresponds to physical reality, which is an observational matter. The connection between the mathematical framework and observational predictions runs through several specific calculations. The Hawking points prediction emerges from calculating how energy released by previous aeon supermassive black hole evaporation would manifest in the current aeon through the conformal transformation. The detailed temperature signatures of Hawking points have been calculated under specific assumptions about the previous aeon black hole population. The predicted properties of cosmic structure in the current aeon, including the spectrum of density variations and the timing of structure formation, have also been calculated. The detailed mathematics is, by every careful description, the engine of testable predictions. Without the specific calculations, CCC would be just a philosophical proposal rather than a scientific framework. With the calculations, CCC becomes a testable alternative to inflation. The framework can be falsified by observations that disagree with its specific predictions. Whether the framework can be confirmed by observations that agree with its specific predictions is, by every careful estimate, the open question. The Penrose-Gazardian collaboration has been the primary group searching for observational evidence of CCC. Vahe Gazardian at the Yerevan Physics Institute in Armenia has been collaborating with Penrose on CCC tests since approximately 2010. Their early papers reported circular patterns in WMAP, cosmic microwave background data, that they interpreted as evidence for CCC. Subsequent papers analyzed Planck data with similar conclusions. The Gazardian-Penrose claimed detections have been disputed by other groups. Andrew Jaffe at Imperial College London, James Zibin at the University of British Columbia, and Douglas Scott, also at the University of British Columbia, have published critical analyses arguing that the apparent circular patterns are consistent with random statistical fluctuations rather than genuine CCC signatures. The debate between the Penrose-Gazardian claims and the critical analyses has continued in the academic literature for over a decade without clear resolution. Each side has, by every careful description, sophisticated statistical arguments. The disagreement comes down to subtle questions about what counts as significant detection in CMB data, with many possible random patterns. The future CMB experiments, particularly CMB-S4 and LiteBIRD, will produce data with higher precision than WMAP or Planck. The improved data should, by every careful estimate, allow more decisive tests of the CCC predictions. If Hawking points are real features of the CMB, they should be detectable with much higher confidence in the improved data. If they are not real, the higher precision data should clearly rule them out. The next several years of CMB observations will, by every careful estimate, substantially advance the CCC question. Beyond the Hawking points, CCC makes other specific mathematical predictions that future observations can test. The framework predicts a specific spectrum of cosmic microwave background polarization that differs from inflationary predictions. The differences are subtle but in principle detectable with sufficient precision. The framework also predicts specific features in the cosmic structure formation history that the next generation of cosmic surveys may be able to detect. Each of these predictions is, by every careful description, a potential test of the CCC framework. The mathematical structure of CCC is, in this sense, both a strength and a vulnerability. The structure is mathematically elegant and conceptually appealing. The structure also makes specific predictions that can be tested observationally. The framework is, in this sense, a model of how alternative cosmological frameworks should be developed if they want to be taken seriously by the broader community. Let's talk about the specific observational predictions of CCC. The framework, as Penrose has developed it, makes several specific predictions about what we should observe in the cosmic microwave background if cyclic cosmology is correct. The most famous of these predictions involves what Penrose has called Hawking points. The reasoning behind Hawking points is, by every careful description, intriguing. Supermassive black holes in the previous cosmic aeon, like the central black holes of every galaxy in the current cosmic era, would have eventually evaporated through Hawking radiation. The evaporation of a supermassive black hole releases an enormous amount of energy over enormously long timescales. The energy is released into the surrounding cosmic medium as photons and other massless particles. By the time the previous aeon ended and the conformal transition to our current aeon began, every supermassive black hole that had ever existed in the previous aeon would have completed its Hawking radiation evaporation. The released energy would have been distributed across an enormous volume of the previous aeon-late universe. Now, here is where Penrose's framework gets specific. Through the conformal rescaling that connects the previous aeon to ours, the energy released by previous aeon supermassive black hole evaporation should manifest as specific localized features in the cosmic microwave background of our current aeon. These features would be approximately circular patterns in the CMB temperature distribution. Each pattern would correspond to a single supermassive black hole that existed in the previous aeon. The size of each pattern would depend on the mass of the corresponding black hole. The pattern would be centered at the position where the black hole existed during its evaporation phase. Penrose has called these predicted features Hawking points, after Stephen Hawking, who originally derived the theory of black hole evaporation. The Hawking points, if they exist, would be one of the most specific and testable predictions of any pre-Big Bang cosmology. Their existence would, by every careful estimate, provide strong evidence that the previous aeon supermassive black holes were real, and that the conformal transition to our current aeon actually happened. Penrose and collaborators have searched for Hawking points in the cosmic microwave background data. The search was led primarily by Vahe Gurzadian, a physicist at the Yerevan Physics Institute in Armenia, who has collaborated with Penrose on CCC analyses since 2010. The team analyzed WMAP and Planck cosmic microwave background data, looking for the specific circular patterns that CCC predicts. In a series of papers published between 2010 and 2020, Gurzadian and Penrose claim to have detected statistically significant concentric circles in the CMB data. The detection was, by every careful description, controversial. Other research groups attempting to confirm the detection have generally not been able to do so. Some analyses have found that the apparent circular patterns are consistent with random statistical fluctuations in the CMB, not evidence for previous aeon features. The status of the Hawking point claim remains, by every honest description, contested. Penrose maintains that the detection is real and that subsequent analyses by other groups have used inadequate methods. Most other cosmologists are skeptical and consider the claimed detection unconfirmed. The debate has continued in the academic literature without clear resolution. Beyond Hawking points, CCC predicts other specific features in the cosmic microwave background. The framework predicts that the CMB should have a specific spectrum of temperature variations that differs from the predictions of inflation. The differences are subtle and require very precise measurements to detect. Current CMB observations are consistent with both inflation and CCC, with the precision not yet sufficient to definitively distinguish between the two frameworks. Future CMB experiments, which we will discuss in more detail later, may be able to make the distinction. CCC also predicts the absence of primordial gravitational waves at the level that simple inflationary models predict. Primordial gravitational waves generated during the inflationary epoch should leave a characteristic polarization pattern in the CMB called B-mode polarization. The BICEP experiments at the South Pole have been searching for B-mode polarization for over a decade, with the BICEP 3 and BICEP array experiments providing the most recent constraints. If inflation produced primordial gravitational waves at the level that many inflationary models predict, the B-modes should already have been detected. They have not been. Whether the non-detection indicates that the simple inflationary models are wrong, or that more elaborate inflationary models predict lower B-mode amplitudes, or that CCC and other alternatives are favoured, is, by every careful estimate, still being analysed. CCC would naturally predict no significant primordial B-modes, since the framework does not invoke inflation. If the BICEP and follow-up experiments continue to fail to detect B-modes, this would be at least suggestive evidence in favour of CCC and against simple inflation. But the absence of evidence is not the same as evidence of absence. The B-mode constraints from current experiments still leave room for many inflationary models that predict lower amplitudes than the simplest cases. The future experiments will tighten the constraints, but a definitive verdict may take many years to emerge. Beyond the cosmic microwave background, CCC makes some other predictions that have been less observationally tested. The framework predicts specific properties of cosmic structure that differ from the inflationary predictions in subtle ways. The growth of cosmic structure over the past 13 billion years should, in CCC, follow a slightly different trajectory than the inflationary models predict. The differences are, by every careful estimate, too small to detect with current observations, but might become detectable with the next generation of cosmic structure surveys, including the Roman Space Telescope, the Vera-Rubin Observatory, and the Square Kilometre Array. CCC also makes specific predictions about the long-term cosmic future. The framework requires the current cosmic era to eventually transition into the long late universe state where all matter has decayed to radiation. This requires either that all currently stable particles eventually decay, or that some currently unknown mechanism converts all mass to massless particles. The standard model of particle physics does not predict the decay of stable particles like the proton. Various theoretical extensions of the standard model do predict proton decay, but no proton decay has ever been observed in the most sensitive experiments, the Super Kamiokande experiment in Japan and the planned Hyper Kamiokande experiment will continue to search for proton decay with increasing sensitivity. If proton decay is eventually detected, it would be at least suggestive that CCC's requirement for a final radiation-dominated state could be achieved. If proton decay continues to not be detected, CC will need to invoke other mechanisms for converting matter to radiation in the deep future. The detailed observational evidence for or against CCC is, by every honest description, mixed. The framework has some claimed evidence in its favour, including the Hawking point detections that Guzardian and Penrose have reported. The framework also has some claimed evidence against it, including the failure of independent groups to confirm the Hawking point detections. The broader observational picture is consistent with CCC as a possibility, but does not definitively support it over the standard inflationary model. The most important future tests are the next generation of cosmic microwave background experiments, the next generation of cosmic structure surveys, and the eventual resolution of the question of whether protons decay. Each of these will provide specific data that will help discriminate between cosmic origin scenarios. By the end of the 2020s, by every careful estimate, the observational situation should be substantially clearer. Whether that clarity will support CCC, support inflation, or support some other framework that we have not yet considered is, by every honest description, the open question. Beyond Penrose's conformal cyclic cosmology, several other pre-Big Bang and cyclic cosmologies have been seriously developed by major physicists. Each framework has its own motivations, its own predictions, and its own challenges. Let's consider them in turn. The Steinhardt-Turok cyclic model is, by every careful description, one of the most fully developed alternatives to inflation. Paul Steinhardt and Neil Turok proposed the framework in 2001 and 2002 in a series of papers published in Physical Review and Science. Steinhardt was, somewhat ironically, one of the original developers of the new inflation model in 1982, working with Andreas Albrecht. He had spent 2 decades developing inflationary cosmology before becoming concerned about specific theoretical problems with the framework. Turok was a professor at the University of Cambridge at the time of the proposal. He later moved to the Perimeter Institute for Theoretical Physics in Waterloo, Canada, where he became director. The Steinhardt-Turok cyclic model is based on ideas from string theory and brane cosmology. The framework proposes that our observable universe is a 3-dimensional brane embedded in a higher dimensional spacetime. The brane periodically collides with another nearby brane, with each collision producing what we observe as a Big Bang. The cosmic cycles are, in this framework, the cycles of brane collisions and subsequent expansion. Between collisions, the cosmic dynamics are dominated by dark energy and slow contraction. The cycles repeat indefinitely, with each cycle lasting trillions of years. The Steinhardt-Turok model addresses several of the same theoretical concerns that motivated Penrose's CCC. The framework avoids the initial singularity by having the universe transition continuously from one cycle to the next. The framework avoids the multiverse implication of inflation. The framework provides a natural explanation for the low entropy at the start of each cosmic cycle, since the entropy is reset by the brane collision. Critics have raised several concerns. The framework relies on specific aspects of string theory that are not yet established. The detailed physics of the brain collision is, by every careful description, complex and difficult to calculate. The framework also requires specific properties of dark energy that may not match observations. Steinhardt has continued to develop and defend the framework in papers and talks. He has been a prominent public critic of inflation, arguing in popular books and articles that the standard inflationary picture has fundamental problems that cyclic cosmology addresses. His 2014 Scientific American article on the multiverse, titled "Pop Goes the Universe," was a particularly influential critique. The Veneziano-Gasparini pre-Big Bang scenario is, by every careful description, another well-developed alternative. The framework was proposed by Gabriele Veneziano at CERN and Maurizio Gasparini at the University of Bari in 1993, with extensive development in subsequent papers. The framework is also based on string theory, but proposes a different mechanism than the Steinhardt-Turok model. In the Veneziano-Gasparini picture, the universe before the Big Bang was in a contracting phase. The contraction reached a minimum size determined by string-theoretic considerations, then transitioned smoothly into the expansion we observe as the Big Bang. The pre-Big Bang phase in this framework was a real cosmic history extending backward in time before the apparent moment of the Big Bang. The framework has been developed in detail and makes specific predictions about cosmic observables. The most distinctive prediction is the spectrum of primordial gravitational waves, which differs from inflationary predictions in characteristic ways. If primordial gravitational waves are eventually detected, the spectrum could distinguish between the Veneziano-Gasparini scenario and inflationary models. The framework also predicts specific features in the cosmic microwave background that future experiments may be able to detect. Loop quantum cosmology is another alternative framework, developed primarily by Abhay Ashtekar at Pennsylvania State University and his collaborators. The framework is based on loop quantum gravity, a proposed quantum theory of gravity that is the main alternative to string theory. In loop quantum cosmology, the cosmic singularity at the Big Bang is replaced by a bounce. The universe before the bounce was contracting. The contraction reached a minimum size determined by quantum gravity effects, then transitioned into the current expansion. The framework, like the Veneziano-Gasparini scenario, predicts a pre-Big Bang cosmic history. The detailed predictions of loop quantum cosmology have been worked out in numerous technical papers. The framework makes specific predictions about the cosmic microwave background that could be tested with future precision experiments. Whether the predictions can be definitively tested is, by every careful estimate, still being determined. The Hartle-Hawking no-boundary proposal is, by every careful description, a different kind of alternative. Proposed by James Hartle at the University of California, Santa Barbara, and Stephen Hawking at the University of Cambridge in 1983. The framework does not propose a cyclic universe, but rather a universe with no boundary in the past. In the no-boundary picture, the question of what came before the Big Bang is not meaningful, because there is no temporal boundary to speak of. The universe is finite in the past, like the surface of a sphere is finite in extent, but has no edge or boundary. The mathematical machinery uses what is called Euclidean quantum gravity, where the time dimension is replaced by an additional spatial dimension in the very early universe. The framework has, by every careful description, philosophical implications that are still being debated. The framework was developed extensively by Hartley, Hawking, and others over several decades. The detailed observational predictions are less specific than CCC or the cyclic models. The framework remains one of several theoretical options for understanding cosmic origins. Beyond these major alternatives, several other frameworks have been proposed. The Penrose-Hameroff orchestrated objective reduction theory, while not specifically a cosmology, has implications for how time and consciousness fit into the universe. The various ekpyrotic models related to but distinct from the Steinhardt-Turok cyclic model propose specific mechanisms for cosmic transitions. The pre-inflationary cosmology models propose that inflation was preceded by a different cosmic phase that explains the inflationary initial conditions. Each framework has its proponents and its critics. Each makes specific predictions that, in principle, can be tested. The collective effort to develop and test pre-Big Bang scenarios has, over the past 3 decades, produced an enormous body of theoretical work. The diversity of frameworks is, by every careful estimate, both a strength and a weakness. It is a strength because it shows that the question of what came before the Big Bang is taken seriously by many capable theorists. It is a weakness because the lack of convergence on a single framework makes it harder to definitively test the alternatives against the standard inflationary model. The standard model, by contrast, has a more uniform theoretical foundation that all its proponents share. Inflation has different specific implementations, but they all share the basic framework of exponential cosmic expansion driven by a scalar field. The pre-Big Bang alternatives have less commonality. They share only the rejection of the standard inflationary picture and the proposal that something existed before the Big Bang. The specific details differ substantially from one framework to another. The cosmological community's response to all these alternatives has been, by every careful description, mixed. Some prominent cosmologists take the alternatives seriously and consider them viable competitors to inflation. Others consider them speculative and prefer to stick with the well-tested inflationary framework. The debate has continued in academic journals and at major conferences for over 2 decades. The recent JWST observations have, in some interpretations, given new life to the alternatives. The unexpectedly active early universe revealed by JWST is, by every careful estimate, difficult to fully reconcile with the simplest inflationary models. Whether the modifications required to make inflation work are more or less plausible than the alternatives is, by every honest description, still being argued. The resolution will require, by every careful estimate, more observations and more theoretical work. The current decade is, in this sense, a particularly important period for the question of cosmic origins. The next generation of experiments will provide data that may finally distinguish between the competing frameworks. Now, let's talk about how the recent JWST observations bear on the question of cosmic origins. The James Webb Space Telescope was not specifically designed to test pre-Big Bang scenarios. It was designed to observe the early universe in infrared light, which it does extremely well. The implications for cosmological theory are derived from the observations rather than being directly tested, but the implications are, by every careful estimate, significant. JWST has, since beginning operations in 2022, produced a steady stream of discoveries about the early universe that the standard inflationary Big Bang model has difficulty explaining in its simplest form. The bright early galaxies, the overgrown supermassive black holes, the rapid chemical enrichment, the cosmic web that was already developed at 1 billion years after the Big Bang, all are observations that push the standard model toward its limits. Each observation pushes the model, The cumulative effect is to make the model less elegant and to open space for alternative frameworks. The most striking of these JWST observations is the population of unexpectedly massive and bright galaxies at very high redshifts. JWST has identified galaxies at redshifts above 10, corresponding to cosmic ages of less than 500 million years after the Big Bang. The most distant spectroscopically confirmed galaxy as of 2026 is MOME 14 at redshift 14.44, corresponding to a cosmic age of approximately 280 million years. These very early galaxies are, in many cases, more massive and more chemically enriched than the standard cosmological model comfortably predicts. The standard model requires multiple generations of stars to have lived, died, and seeded the cosmic gas, with heavy elements before the chemically enriched galaxies that JWST observes could have formed. The available cosmic time is, by every careful estimate, very tight for this entire chain of events. The standard model can produce the observed galaxies with appropriate adjustments to star formation efficiency and stellar feedback, but the adjustments push the model to its limits. The overgrown supermassive black holes are another striking observation. JWST has identified supermassive black holes at cosmic epochs where the standard accretion physics suggests they should not yet exist. The little red dots that we have explored in a previous evening are populated by black holes of millions to hundreds of millions of solar masses at redshifts of 6 to 9. The Virgil galaxy hosts a black hole more than 100 times more massive than the local M-bulge relation would predict for its host galaxy. The standard model can produce these black holes through direct collapse and rapid accretion, but the requirements are stringent. The cosmic web at 1 billion years after the Big Bang, mapped in detail by the Cosmos Webb survey released in May 2026, shows that the basic filamentary structure was already in place. The proto-clusters in the map were already assembling. The voids were already opening up. The basic architecture of cosmic structure was set up very early in cosmic history. The standard model can produce this early cosmic web, but the timing is, by every careful estimate, tight. In a pre-Big Bang cosmology, some of these features could be inherited from the previous cosmic state. Density fluctuations, dark matter halos, and even possibly some primordial stellar populations could survive a transition from one cosmic era to the next, depending on the specific mechanism of the transition. The early universe in pre-Big Bang scenarios would not start from a clean blank slate, but from an already developed state that the previous era had produced. This kind of inherited structure could, in principle, explain why JWST is finding galaxies that look more developed than the standard model predicts. The galaxies would have had longer effective evolutionary timescales because they would have started from non-trivial initial conditions rather than from purely cosmological initial conditions established by inflation. The compressed apparent timeline from the Big Bang to the JWST observations would, in this picture, be less restrictive. The detailed mechanism by which structure could survive a cosmic transition depends on the specific pre-Big Bang framework. In Penrose's CCC, the conformal rescaling preserves the geometric structure of the previous aeon late universe. The energy released by previous aeon supermassive black holes appears as the Hawking points in our cosmic microwave background. Whether other structural features could also survive is, by every careful estimate, still being worked out. Penrose has argued that some features of cosmic structure might be inherited, but the detailed predictions are not fully developed. In the Steinhardt Turok cyclic model, the brain collision that produces our observed Big Bang is, by every careful description, a violent event that should erase most previous cycle structure. But the framework allows for the possibility that some structural information could be transferred across the cycle boundary. The detailed predictions are, by every honest description, still being worked out. In the Veneziano-Gasparini pre-Big Bang scenario, the cosmic contraction phase that preceded the Big Bang would have produced specific structural features that could survive into the current expansion phase. The framework predicts a specific spectrum of primordial gravitational waves that differs from inflationary predictions in characteristic ways. If primordial gravitational waves are eventually detected, the spectrum could distinguish between the scenarios. Penrose himself has, in various recent papers and public lectures, drawn explicit connections between his CCC framework and the JWST observations. He has argued that some of the structures JWST is finding are more naturally explained as inheritances from a previous cosmic aeon than as products of the standard inflationary evolution. Whether his interpretation is correct depends on technical details of the CCC framework that are still being worked out. But the connection is, by every careful description, being seriously discussed in the cosmological literature. Steinhardt and his collaborators have made similar arguments for the cyclic model. They have argued that the cyclic framework can, in some interpretations, accommodate the JWST observations more naturally than the standard model. The detailed predictions are, by every careful estimate, still being worked out, but the basic argument is that inherited structure from a previous cycle could explain the unexpectedly developed early universe that JWST is revealing. Other proponents of pre-Big Bang scenarios have made similar arguments. The combined effect is, by every careful description, that the alternative frameworks are getting more serious attention than they did before JWST began operations. The standard model is being defended through modifications. The alternatives are being explored through detailed comparisons with the JWST data. The debate is, by every careful estimate, more active than it has been in years. The cosmological community is, by every honest description, divided on the implications of the JWST observations. Some researchers see the observations as motivating new physics that may include pre-Big Bang scenarios. Others see the observations as straightforwardly consistent with the standard model, with appropriate astrophysical modifications. The exact line between these positions is, by every careful description, drawn differently by different researchers. The eventual resolution of this debate will require, by every careful estimate, more observations and more theoretical work. The next several years of JWST observations will continue to refine the picture of the early universe. The Roman Space Telescope, scheduled for launch in 2027, will add complementary observations. The Vera Rubin Observatory, which began operations in 2025, will provide further data. The Square Kilometre Array, currently under construction in South Africa and Australia, will contribute. The combined dataset over the next decade will, by every careful estimate, be substantially richer than what we currently have. Whether this richer dataset will support the standard inflationary Big Bang model with modifications or will require more fundamental revisions of the framework is, by every honest description, the open question. The JWST observations are, in this sense, one of the most important pieces of evidence in the broader debate about cosmic origins. They are not, by themselves, decisive, but they are part of a growing body of evidence that the standard cosmological model may need substantial revision. Whether the revisions will involve pre-Big Bang scenarios or stay within the inflationary framework is the question that the next decade of observations should help to resolve. Let's consider what the future cosmic microwave background experiments might reveal about cosmic origins. The cosmic microwave background is, by every careful description, our most direct probe of conditions in the very early universe. The temperature variations across the sky encode information about cosmic density, variations at the moment of CMB emission, approximately 380,000 years after the Big Bang. The polarization of the radiation carries additional information about cosmic conditions and potentially about gravitational waves from the inflationary epoch or from alternative cosmic origins. The detailed analysis of the CMB has, by every careful estimate, been one of the most productive enterprises in cosmology over the past 3 decades. The COBE satellite mission, launched in 1989, was the first to measure the CMB temperature and detect its tiny variations across the sky. The WMAP satellite mission, operating from 2001 through 2010, refined the temperature variation measurements and produced the first detailed map of CMB anisotropies. The Planck satellite mission, operating from 2009 through 2013, produced the most precise CMB measurements to date, with temperature and polarization data that has constrained cosmological parameters to high precision. The next major step in CMB observations is the CMB-S4 experiment. CMB-S4 is a planned ground-based observatory that will combine arrays of detectors at the South Pole and in northern Chile. The total number of new detectors will be in the hundreds of thousands, far more than any previous CMB experiment. The experiment is being developed by a consortium of more than 100 institutions with leadership from the Department of Energy's Fermilab and Argonne National Laboratory, the National Science Foundation, and major universities including Berkeley, Stanford, and Chicago. The total cost is approximately $750 million. The science program is expected to begin in the late 2020s. CMB-S4 will measure the CMB temperature and polarization with much higher precision than any previous experiment. The improvement in sensitivity for B-mode polarization is, by every careful estimate, one of the most important advances. B-mode polarization is the specific pattern of polarization that primordial gravitational waves from the inflationary epoch should leave on the CMB. The detection of primordial B-modes would be one of the most direct possible pieces of evidence for inflation. CMB-S4 will be sensitive enough to detect B-modes for inflation models that produce gravitational waves at energies above approximately 10 to the 16 GeV. If inflation occurred at these higher energy scales, the B-modes should be detectable. If inflation occurred at lower energy scales, or if some pre-Big Bang alternative is the correct framework, the B-modes will be absent or below the CMB-S4 detection threshold. The detection or non-detection of primordial B-modes will, by every careful estimate, be one of the most significant cosmological observations of the next decade. The LiteBIRD satellite mission, planned by the Japan Aerospace Exploration Agency for launch in 2029 or shortly after, will provide complementary CMB measurements from space. LiteBIRD will conduct an all-sky survey at multiple frequencies with sensitivity to B-mode polarization that complements the CMB-S4 ground-based measurements. The mission is being developed under the leadership of Masashi Hazumi at the High Energy Accelerator Research Organization in Tsukuba, Japan. The international collaboration includes researchers from Japan, the United States, Europe, and Canada. The total cost is approximately $300 million. The combination of CMB-S4 and LiteBIRD will, by every careful estimate, provide the most decisive tests of inflationary versus pre-Big Bang cosmologies that have ever been conducted. Detection of primordial B modes at the level that simple inflation predicts would be strong evidence for inflation. Non-detection at the sensitivity of these experiments would, by every careful estimate, force significant revisions to inflationary models or possibly motivate alternatives. Penrose's CCC and the other pre-Big Bang scenarios make different predictions for B-mode polarization. CCC predicts essentially no primordial B modes, since the framework does not invoke inflation. The Steinhardt-Turok cyclic model similarly predicts no significant primordial B modes. The Veneziano-Gasparini pre-Big Bang scenario predicts a specific B mode spectrum that differs from inflationary predictions. Loop quantum cosmology predicts modified B mode spectra. Each framework has its own signature predictions that future B mode measurements could test. Beyond B modes, the next generation of CMB experiments will refine measurements of other cosmological observables. The detailed shape of the CMB power spectrum will be measured with much higher precision. The patterns of CMB temperature variations on small angular scales will be characterized. The polarization patterns at multiple angular scales will be measured. Each of these refinements adds constraints on cosmological models. The Simons Observatory, currently under construction in Chile and expected to begin science operations in 2026 or 2027, is an intermediate-scale CMB experiment that will provide measurements at sensitivity between Planck and CMB-S4. The Simons Observatory is being led by researchers at Princeton University, the University of California, Berkeley, and other major institutions. The total cost is approximately $300 million. The early Simons Observatory results will, by every careful estimate, provide significant new constraints on cosmological models even before CMB-S4 begins operations. The PICO satellite mission concept, proposed for the late 2030s, would extend CMB measurements to even higher precision than CMB-S4 and LiteBIRD. PICO would be a NASA-led space mission with European and Japanese collaborators. The mission has not yet been formally approved, but the science case has been developed in detail. If approved, PICO would provide the most precise CMB measurements possible from space, with sensitivity to even the lowest amplitude primordial gravitational waves that current models predict. Beyond the cosmic microwave background, other future cosmological observations will contribute to the debate about cosmic origins. The cosmic Webb mapping work that we discussed in a previous evening will continue with the Roman Space Telescope, the Vera Rubin Observatory, the Square Kilometre Array, and Euclid. The cosmic Webb measurements provide independent constraints on cosmological parameters that complement the CMB measurements. Different combinations of measurements provide different constraints, with the eventual cosmological model needing to be consistent with all of them. The detection of primordial gravitational waves directly through space-based gravitational wave observatories is another long-term goal. The proposed LISA Big Bang Observer concept would, in principle, be sensitive enough to detect primordial gravitational waves from the inflationary epoch directly, rather than indirectly through their imprint on the CMB. The mission concept is in early development. If realized, it would provide a completely different way to test inflationary versus pre-Big Bang cosmologies. The eventual resolution of the cosmic origins question will require, by every careful estimate, decades of additional observational and theoretical work. The current decade is one stage in a much longer scientific endeavour. The CMB experiments, the cosmic Webb surveys, the JWST observations, and the future gravitational wave observatories will all contribute. The eventual answer, when it emerges, will likely involve the synthesis of evidence from many different directions. Whatever the eventual answer is, the work being done now is laying the foundation for that synthesis. The CMB-S4 and LiteBIRD experiments in particular are designed to be definitive tests of inflationary cosmology versus the major alternatives. Their results in the late 2020s will, by every careful estimate, significantly clarify the cosmological picture. Whether they will confirm inflation or motivate the alternatives is the question that the next decade of CMB observations should help to resolve. The recent cosmological tensions add another layer to the debate about cosmic origins. Over the past decade, multiple independent observations have revealed disagreements between different measurements of cosmological parameters. These tensions are, by every careful description, not catastrophic for the standard cosmological model, but they are persistent and growing in statistical significance. They suggest that something in the standard picture may need revision. The most famous of these tensions is the Hubble tension. The Hubble constant is the parameter that describes the current rate of cosmic expansion. It can be measured in multiple independent ways. Local measurements using distance ladder techniques calibrated through Cepheid variable stars and Type-Ia supernovae give a value of approximately 73 kilometers per second per megaparsec. Measurements derived from the cosmic microwave background using the Planck satellite data and the standard cosmological model give a value of approximately 67 kilometers per second per megaparsec. The two measurements disagree by more than 10%, with statistical significance well beyond the threshold for a discovery. Adam Rees at Johns Hopkins University has been the leading advocate for the reality and importance of the Hubble tension. Rees and his SHOES collaboration have, over the past decade, refined the local Hubble constant measurement multiple times. Each refinement has confirmed the disagreement with the CMB-based measurement. The disagreement has persisted despite multiple independent checks. The Hubble tension is, by every careful description, one of the major unsolved problems in modern cosmology. The Hubble tension could be resolved in several different ways. The simplest possibility is that one or both of the measurements has a systematic error that has not yet been identified. This is, by every careful estimate, possible, but increasingly unlikely as the measurements have been checked and rechecked. The more interesting possibility is that the disagreement reflects genuine new physics in the cosmological model. Various proposals have been made for new physics that could resolve the Hubble tension. Early dark energy, where a transient dark energy component existed before the cosmic microwave background was emitted, is one of the most actively studied proposals. Modified gravity, where the laws of gravity differ slightly from general relativity, is another. Various exotic neutrino properties have also been proposed. Each proposal makes specific predictions that can be tested. None has yet been definitively confirmed. The relevance of the Hubble tension to pre-Big Bang cosmology is, by every careful description, indirect but real. If the resolution of the Hubble tension requires new physics, that new physics might also have implications for cosmic origins. Some of the proposed resolutions involve modifications to the very early universe that could be more naturally compatible with cyclic or pre-Big Bang scenarios than with standard inflation. The connections are subtle and still being worked out. The S8 tension is another major cosmological discrepancy. S8 is a parameter that describes how clumpy cosmic structure is on large scales. The CMB-based measurement of S8 from the Planck satellite gives a value that is somewhat higher than the values derived from weak gravitational lensing measurements of cosmic structure. The Kilo-degree survey at the European Southern Observatory and the Dark Energy Survey at the Cerro Tololo Inter-American Observatory have both produced S8 measurements consistent with each other but disagreeing with the Planck value. The statistical significance of the disagreement is, by every careful estimate, less than the Hubble tension but still substantial. Like the Hubble tension, the S8 tension could be resolved by either systematic errors or new physics. The proposed resolutions overlap with the Hubble tension resolutions. Early dark energy can affect both tensions. Modified dark matter properties can affect both. The exotic neutrino proposals can affect both. The fact that multiple tensions might share a common resolution is, by every careful description, encouraging from a theoretical perspective. It suggests that the standard model may have specific issues that, once identified, will resolve multiple problems simultaneously. The DESI dark energy results from 2024 and 2025 add another tension. The Dark Energy Spectroscopic Instrument has been measuring the cosmic expansion history through baryon acoustic oscillations. The DESI Year 1 results, released in April 2024, hinted that dark energy may be evolving over cosmic time rather than remaining constant. The Year 2 results, released in 2025, strengthened the hints. The statistical significance is, by every careful estimate, in the 3 to 4 sigma range, suggestive but not definitive. The implication of evolving dark energy is, by every careful description, profound. If dark energy is evolving, then the standard cosmological constant interpretation of dark energy is wrong. The cosmic future depends on the specific form of the evolution. If dark energy is weakening, the cosmic future could be very different from the simple heat-death scenario. If dark energy is strengthening, the cosmic future could be a big rip in which dark energy eventually overcomes every other force. The pre-Big Bang implications are also significant. Some of the proposed dark energy evolution scenarios can be embedded naturally in cyclic cosmologies. Others can be embedded in inflationary frameworks with modifications. The detailed comparisons are, by every careful estimate, still being worked out. The JWST observations of an unexpectedly active early universe add yet another tension. The bright, early galaxies, the overgrown, supermassive black holes, the rapid chemical enrichment, the cosmic web that was already developed at 1 billion years after the Big Bang, all are observations that push the standard inflationary Big Bang model. Each of these tensions is, by itself, moderate in size. Together, they form a pattern. The pattern suggests that the standard model is not the final word. Many cosmologists have, in 2025 and 2026, started speaking openly of a possible cosmological crisis. The term crisis is used in a specific historical sense, referring to a period of theoretical and observational disagreement that motivates fundamental revisions to a scientific framework. Past examples include the crisis in classical mechanics that led to relativity and quantum mechanics in the early 20th century, and the crisis in 19th century physics that led to the discovery of dark matter and dark energy in the late 20th century. Whether the current cosmological tensions constitute a true crisis is, by every honest description, contested. Some researchers see the tensions as fundamental and pointing toward new physics. Others see them as manageable within the standard framework. The eventual resolution will, by every careful estimate, only become clear over the next several years as the various measurement programs continue and the statistical significance of the tensions becomes clearer. For pre-Big Bang cosmology specifically, the tensions are at least suggestive. If the standard inflationary model needs significant revision to accommodate multiple independent tensions, that opens space for alternative frameworks. The alternatives, including Penrose's CCC, the Steinhardt-Turok cyclic model, and the various pre-Big Bang scenarios, become more competitive against the standard model as the standard model's problems accumulate. The cosmological community has, by every careful description, become more open to seriously considering alternatives than it was a decade ago. This is, by every honest description, partly because of the accumulated tensions and partly because of the JWST observations that are putting additional pressure on the standard model. The eventual resolution of all this is, by every careful estimate, one of the most exciting open questions in modern science. The cosmological model that emerges from the current period of tension and debate will, by every careful estimate, be more comprehensive than the current standard model. It will incorporate everything the current standard model gets right and will also accommodate the additional observations that the current model has difficulty with. Whether it will involve pre-Big Bang scenarios in any form is the question we are about to address in our final discussion of where the field is going. The philosophical implications of pre-Big Bang cosmology are, by every careful description, profound. If the universe has always existed, going through cycles or transitions, then the question of what came before becomes meaningful in ways that the standard Big Bang model does not allow. The cosmic past extends, in pre-Big Bang scenarios, beyond the moment 14 billion years ago that we call the Big Bang. The actual cosmic timeline could extend back through enormous timescales, potentially infinite. This philosophical extension of cosmic time has implications for various deep questions that humans have asked for thousands of years. The question of why the universe exists, traditionally a question for philosophy and theology, becomes potentially answerable through pre-Big Bang physics. The question of cosmic origin in particular may not have a definite answer if the universe has always existed in some form. The question of cosmic purpose, whether the universe has a direction or meaning, may need to be reconsidered in cyclic frameworks where the universe repeatedly arrives at the same kinds of states. The connection to traditional religious and philosophical questions about cosmic origins is, by every careful description, worth noting. Many religious traditions teach that the universe had a definite beginning, with that beginning often associated with divine action. The standard Big Bang model has been, in some interpretations, broadly compatible with these traditional views. Pre-Big Bang cosmologies, by contrast, suggest a universe that has always existed in some form. The implications for traditional theological views are, by every honest description, significant, although the exact implications depend on specific theological frameworks. Different religious traditions handle the question of cosmic beginning differently, and the implications of cyclic cosmology vary accordingly. The philosophical implications of pre-Big Bang scenarios should not, by every careful description, drive the scientific evaluation. The scientific question is what the observations actually show. The philosophical implications follow from whatever the science establishes. If the data eventually favors a pre-Big Bang cosmology, the philosophical implications will need to be worked out. If the data continues to favor the standard model with modifications, the philosophical landscape will be different. The multiverse connection is, by every careful estimate, particularly significant. The standard inflationary cosmology, in most of its specific implementations, naturally produces a multiverse of inflating bubble universes. Each bubble universe could, in principle, have different physical properties. The multiverse picture has been controversial since it was first proposed in the late 1980s and early 1990s. Some physicists embrace the multiverse as a natural consequence of inflation. Others find the multiverse philosophically uncomfortable and prefer cosmological frameworks that avoid it. Pre-Big Bang scenarios offer different perspectives on the multiverse question. Penrose's CCC does not naturally produce a multiverse. Each cosmic aeon in CCC is a single universe with definite properties. The cycles produce successive universes through cosmic time, but not the parallel universes of inflationary multiverse models. Some physicists find this aspect of CCC philosophically appealing. The Steinhardt-Turok cyclic model similarly avoids the inflationary multiverse, although it permits its own kind of multiverse through the brane collision dynamics. Steinhardt has been particularly vocal about the multiverse problem with inflation, arguing in popular articles and books that the multiverse implication is a serious problem with standard inflationary cosmology. The anthropic principle is, by every careful description, related to the multiverse question. The anthropic principle, in its various forms, suggests that the specific properties of our universe are what they are because we exist as observers within it. Other possible universes, with different properties, would not contain observers, and so would not be observed. The principle has been controversial since it was first formulated in detail by Brandon Carter at the University of Cambridge in the 1970s. The anthropic principle has been used to explain various apparently fine-tuned features of our universe. The specific value of the cosmological constant, for example, can be explained anthropically by arguing that universes with significantly different cosmological constants would not contain observers. The specific values of the fundamental physical constants can be similarly explained. The anthropic principle is, by every honest description, not a satisfying explanation for many physicists. The principle does not predict specific values of physical parameters. It only constrains them to be compatible with the existence of observers. The specific values within the compatibility range remain unexplained. Pre-Big Bang cosmologies offer alternative perspectives on apparent fine-tuning. In Penrose's CCC, the conditions at the start of each aeon are determined by the dynamics of the previous aeon. The conditions are not free parameters that can be chosen arbitrarily. They are constrained by the cosmic dynamics. Whether this constraint is sufficient to explain the specific values we observe is, by every careful estimate, an open question. In the Steinhardt-Turok cyclic model, the conditions are similarly constrained by the dynamics of the cosmic cycles. The framework potentially provides a deterministic explanation for the values of cosmic parameters, although the detailed predictions are still being worked out. The implications for human meaning and purpose are, by every careful description, philosophical questions rather than scientific ones, but they connect to the broader cultural significance of cosmology. Cosmological models shape how humans think about their place in the universe. The Big Bang model placed humans in a universe with a definite beginning and a long subsequent evolution. The pre-Big Bang scenarios, if they prove correct, would place humans in a universe with no definite beginning, just an infinite sequence of cosmic states. The change in perspective is, by every honest description, significant. The deep cosmic future is, in pre-Big Bang scenarios, also a deep cosmic past. The universe that will eventually exist after our current era ends in heat death, or some similar terminal state will, in cyclic frameworks, be the universe that gives rise to the next cosmic cycle. The cosmic story does not end with our era, it continues in some form indefinitely. The implications for thinking about cosmic time are, by every careful description, profound. The time scales involved in pre-Big Bang cosmology are also worth pausing on. The cosmic cycles in CCC last enormously long. The current cosmic era will, by every careful estimate, eventually transition into the next cycle only after timescales much longer than the current age of the universe. The cosmic timeline in this sense dwarfs human history by factors that are difficult to comprehend. We are living in what is, on the cosmic timescale, an early period of the current cycle. The vast majority of the cycle's duration is still ahead. Whatever cosmic events define the end of the current cycle and the start of the next will be observed, if at all, by beings vastly different from ourselves. Or perhaps by no observers at all if the cosmic timescales involved exceed the persistence of any kind of complex structure. The patient work of human cosmology in this sense is taking place in a tiny window of an enormously long cosmic history. The detailed picture we are developing now will, by every careful estimate, be one foundation among many for whatever future cosmic civilizations may emerge in our cycle or in future cycles. The question of cosmic origins is, in this larger context, a question that may be asked again and again in different cosmic cycles by different observers with potentially different answers each time. Whether there is a single objective truth about the cosmic origin or whether the question itself shifts in cyclic frameworks is, by every honest description, philosophically uncertain. Let's look at where the cosmological debate about cosmic origins is heading over the next decade. The combination of new observational programs, the persistent cosmological tensions, the recent JWST surprises, and the continued theoretical work on pre-Big Bang alternatives is, by every careful estimate, setting up a particularly productive period for cosmology. The next decade may be more transformative for our understanding of cosmic origins than any decade since the development of the standard inflationary model in the early 1980s. The major observational programs that will contribute to the debate are now mostly identified. JWST will continue operations through the late 2020s and possibly into the 2030s. The telescope's nominal mission lifetime is 5 years, but the actual operational lifetime depends on the propellant remaining for orbit maintenance. Current estimates suggest JWST may operate until 2030 or later. The continued JWST observations of the early universe will add to the picture with the Cosmos Webb cosmic web map and the various deep galaxy surveys being supplemented by additional follow-up programs. The Roman Space Telescope, scheduled for launch in 2027, will conduct the wide-area cosmological surveys that complement JWST's deep observations. The Vera Rubin Observatory, which began operations in 2025, will produce the most complete optical survey of cosmic structure ever conducted, with its 10-year mission running through approximately 2035. The square-kilometre array, currently under construction, will provide radio observations of cosmic structure starting in the late 2020s. The Euclid Space Telescope is already operating and will produce results through 2029 and beyond. Each of these surveys provides complementary measurements that will refine the cosmological picture. The CMB experiments are equally important. CMB-S4 will be the most sensitive CMB observatory ever built, with operations expected to begin in the late 2020s. LiteBIRD will provide complementary space-based CMB measurements starting in 2029 or shortly after. The Simons Observatory is already operating and producing results. The combined CMB data over the next decade will refine the inflationary versus pre-Big Bang test substantially. The detection or non-detection of primordial B modes will, by every careful estimate, be one of the most decisive cosmological observations possible. Beyond the major surveys and CMB experiments, several other observational programs contribute. The proton decay search at Super Kamiokande in Japan and the planned Hyper Kamiokande experiment continue. The dark matter direct detection experiments, including LZ at the Sanford Underground Research Facility in South Dakota and Panda X in China, continue. The accelerator experiments at CERN, including the Large Hadron Collider and its planned high luminosity upgrade, continue. Each of these provides constraints that bear on cosmological models. The theoretical work continues alongside the observations. Penrose, Steinhardt, and the other major advocates of pre-Big Bang scenarios continue to refine their frameworks and to engage with the data. The defenders of standard inflation continue to develop refinements to the inflationary framework that can accommodate the new observations. The broader theoretical community continues to explore alternatives that have not yet been fully developed. The cosmological community has, by every careful description, become more open to considering alternatives than it was a decade ago. The combination of observational pressure from the various tensions and theoretical pressure from the pre-Big Bang frameworks is producing serious discussion of fundamental cosmological questions. Conferences dedicated to cosmic origins are held regularly at major institutions worldwide. The Aspen Center for Physics, the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara, the Institute for Advanced Study in Princeton, and the various European Theoretical Physics Institutes have all hosted dedicated workshops on cosmic origins in recent years. The papers being produced are, by every careful estimate, substantially more sophisticated than the papers from a decade ago. The debate has, in this sense, matured considerably. The most likely outcome of the next decade is, by every careful estimate, a substantial refinement of the standard cosmological model, rather than a wholesale replacement. The standard model has too many successful predictions to be discarded entirely, but the modifications required to accommodate the observations may be substantial. Whether the modifications will involve pre-Big Bang scenarios or stay within the inflationary framework is, by every honest description, the open question. Several specific scenarios for how the debate might resolve are worth considering. The first scenario is that primordial B modes are detected by CMB-S4 or LiteBIRD at the level that simple inflation predicts. This would be strong evidence for inflation and would, by every careful estimate, largely close off the pre-Big Bang alternatives. The standard model would be confirmed with possibly minor modifications to accommodate the various tensions. This is, by every careful description, the outcome that most of the cosmological community would expect if forced to make a prediction. The second scenario is that B modes are not detected at the sensitivity of the next generation experiments. This would be problematic for simple inflation and would force significant revisions. Either more elaborate inflationary models would be required, or the alternatives would become more competitive. The non-detection of B modes alone would not prove that the alternatives are correct, but it would weaken the standard inflationary case considerably. The third scenario is that the cosmological tensions become so severe that they force fundamental revisions to the standard model regardless of what the CMB experiments find. The Hubble tension, the S8 tension, the d-psi dark energy hints, and the JWST early universe surprises together might require modifications that go beyond inflation. In this scenario, pre-Big Bang frameworks might become more attractive as part of the broader revision. The fourth scenario is that some entirely new framework, not yet fully developed, emerges as the best explanation for the combined observations. The history of physics is full of unexpected theoretical developments that resolved previously intractable problems. The possibility of an entirely new cosmological framework cannot be ruled out. Whichever scenario plays out, the next decade will be, by every careful estimate, one of the most exciting periods in cosmology in many decades. The combined observational and theoretical effort is unprecedented in its scope and ambition. The resources being devoted to cosmological research are, by every careful description, substantial. The total funding for the major observational programs and the supporting theoretical work over the next decade is, by every careful estimate, in the tens of billions of dollars. The investment reflects the priority that the global scientific community places on understanding cosmic origins. The eventual scientific return justifies, by every careful estimate, the substantial investment. The understanding that will emerge from all this work will be, by every careful estimate, far deeper than what we currently have. We will know by the early to mid-2030s whether inflation is correct or whether the pre-Big Bang alternatives need to be taken more seriously. We will know whether the cosmological tensions reflect new physics or systematic measurement errors. We will know whether the JWST early universe surprises require fundamental revisions or can be accommodated within the standard framework. The cosmic origins question in this sense may finally be approaching a resolution after decades of theoretical and observational work. Whether the resolution will involve pre-Big Bang scenarios in any form is, by every honest description, still uncertain. But the question itself is now being addressed seriously, with substantial resources, by a broad scientific community. That is, by every careful description, more than has been true at any previous moment in the history of cosmology. The question of whether the Big Bang was truly the beginning of everything or just one moment in a much longer cosmic history is, by every careful description, one of the deepest questions human beings have ever asked. Different cultures throughout history have given different answers, drawing on religion, philosophy, mythology, and various intuitive frameworks. Modern cosmology has, over the past century, transformed the question from a purely philosophical one into an observational one. The Big Bang model emerged from observations, was refined through theoretical work, and became the standard cosmological framework. The pre-Big Bang alternatives, including Penrose's Conformal Cyclic Cosmology, are also being developed through a combination of theoretical work and observational tests. The question is, in this sense, no longer a matter of pure speculation. It is a matter of careful science. The Roger Penrose, who proposed CCC at the age of 74 and who continues to refine the framework into his 90s, is one of the great theoretical physicists of our era. His work on black hole singularities won him the Nobel Prize in 2020. His mathematical contributions span from twistor theory to the Penrose tiles to the conformal compactification of spacetime. His framework for cyclic cosmology, whether correct or not, has forced the broader cosmological community to seriously consider whether the Big Bang was truly the beginning or just one event in a much longer cosmic history. The framework has, by every careful description, made the question respectable in a way that it was not a few decades ago. The JWST observations of an unexpectedly active early universe have added new urgency to the debate. The bright early galaxies, the overgrown supermassive black holes, the rapid chemical enrichment, the cosmic web that was already developed at 1 billion years after the Big Bang, all push the standard inflationary model toward its limits. Whether the modifications required to make the standard model work are simpler than the pre-Big Bang alternatives is, by every honest description, increasingly unclear. The cosmological community will, over the next decade, work through this question with the help of the new observational programs. CMB-S4 and LiteBIRD will provide the most decisive tests of inflation. Roman, Rubin, SKA, and Euclid will refine the cosmic structure measurements. JWST will continue producing surprises. The combined dataset will, by every careful estimate, allow much sharper conclusions about cosmic origins than are currently possible. By the early 2030s, we should know whether the Big Bang was truly the beginning of everything or whether something existed before. Whichever answer emerges, the question will have been addressed with the most powerful tools that human civilization has ever devoted to a single scientific problem. The fact that we can ask this question and seriously hope to answer it is itself one of the more remarkable features of our cosmological era. We are, in some sense, the first generation in history with both the observational tools and the theoretical frameworks to seriously address what came before the Big Bang. Future generations will inherit whatever conclusions we reach. The understanding we develop now will be the foundation for further refinement and exploration. The work is, by every honest description, profound. For tonight, the cosmic question remains open. The Big Bang might be the beginning of everything, or it might be one event in a much longer cosmic history that extends back through cycles, transitions, or other phenomena that we are only beginning to understand. Roger Penrose's Conformal Cyclic Cosmology proposes the latter. The Steinhardt-Turok cyclic model proposes something similar. The various pre-Big Bang scenarios from string theory and loop quantum gravity propose related possibilities. The standard inflationary model continues to be the dominant framework, but is not unchallenged. The cosmic microwave background as you look up at the dark night sky is glowing faintly in every direction at a temperature of 2.725 degrees above absolute zero. The radiation has been propagating freely since approximately 380,000 years after the Big Bang. The pattern of tiny temperature variations across this radiation encodes information about the conditions in the very early universe. Whether those conditions reflect inflation or something else is still being determined. The cosmic web, threading through the entire observable universe and now mapped in unprecedented detail by JWST, extends throughout cosmic space. The galaxies arranged along the filaments are the visible traces of an invisible architecture. Whether that architecture was set up by inflation or by the conformal transition from a previous cosmic aeon is, by every careful estimate, an open question. The deep cosmic future, the eventual heat death or big rip or other ending that awaits the universe depends on dark energy properties that are still being measured. Whether that ending is the absolute end of cosmic history or just the prelude to another cycle is, by every honest description, also an open question. We are, in this sense, living at a particularly interesting moment in the history of cosmology. The questions being asked are profound. The tools available to answer them are unprecedented. The community working on them is large, talented, and engaged. The answers, when they emerge over the coming years, will reshape our understanding of where the universe came from and where it is going. The Big Bang might or might not have been the beginning. The patient work of cosmology will, by every careful estimate, eventually tell us.